In this video, we're going to discuss the idea of differentiability and how that relates to the approximation idea of a function at a given point. And so just start with a particular example here. Recall this is the kind of problem we could have looked at in class. The function f of x is equal to x to the fourth, and I've chosen a specific value of x that I'm interested in, let's say 2. And this is given info. Okay, you're given a function and a point of interest. And we know from the power rule, right, that the derivative of this function is equal to the derivative of x to the fourth is 4x cubed. Okay? And we know where that 4x cubed comes from. We know that it comes from the f of x plus h expansion of the function. And from Pascal's triangle, okay, there I've computed Pascal's triangle. This is n is equal to 0, n equal to 1 power, so you're finding x plus h to the first. This is n equal 2, n equal 3, n equal 4, which means I'm trying to compute x plus h to the fourth power. And we know from Pascal's triangle that this is going to be 1 x to the fourth plus 4x cubed times h plus 6x squared h squared plus 4x to the first h cubed plus 1 h to the fourth. So there's this rather longish looking formula, and what I'm particularly seeing here is that f of x plus h, 1x to the fourth, is the same as the function f of x. 4x cubed was our derivative, and that's being multiplied by h. So what we're seeing here is that the function f of x plus h is equal to the function evaluated at x plus the derivative evaluated at x times h plus higher terms in h. Okay, and these are all the higher terms in h. Notice that they all have powers of on the h of higher than 1. So h squared, h cubed, and h to the fourth are the higher powers in h. Okay? Now what do we do with this kind of formula? What does this formula say? So notice, for example, that if you let x value be the point that you're interested in, then f of 2 plus h is going to be the function evaluated at 2 plus f prime of 2 times h plus higher terms. Okay, and those higher terms, I'm just going to go up here to the function, put in 2, f of 2 is equal to 16, f prime of 2, 2 cubed is 8, so that would be 32 times h. I'm putting 2 into 6x squared, so that would be 4 times 2 is 24h squared. Putting in 2 for x here, that'd be 8h cubed, and then there's no x's here, it's 1h to the fourth. Okay? So, what we're looking at here is 2 plus h to the fourth power is given by exactly this formula. Okay? Now how do we use this formula? What if, for example, that h is equal to 0.1? Then what you're finding is that 2 plus 0.1 to the fourth power is equal to 16 plus 32 times 0.1 plus 24 times 0.1 squared plus 8 times 0.1 cubed plus 1 times 0.1 to the fourth power. Okay? So what we're saying here is that the function evaluated at 2.1, that is this thing, function evaluated at 2.1 is 2.1 to the fourth power. Okay, that's what we're seeing right here. And this thing on the other side of the equal sign tells you what the answer is. 2.1 to the fourth power is going to be 16 plus 1/10 of 32 is 3.2 plus, and now I'll need to go to a calculator to compute the higher terms. So I'm going to go over here to my calculator, okay, which is over here on the side of the screen. and I'm going to put 24 times 0.01 squared, right? 24 times 0.1 squared, okay? Which gives me 0.24, okay? I think I'm seeing a pattern here. 0.01 cubed should be 0.0001, and then multiply that by 8, and you should get 0.008. Oh, that's cubed. I'm sorry, 0.1 cubed. You should get 0.008. Okay? And then 0.1 to the fourth is 0.0001. Okay? So now this formula on the right tells us that 2.1 to the fourth power is equal to 16 plus 3.2 is 19.2 plus some extra stuff, the higher terms, 0.24. Let me just add those together with my calculator here. 0.24 plus 0.008, sorry, 0.008 plus 0.0001. And you get 0.2481. So now what we're seeing here is that 2.1 to the fourth power is 19.2 plus those terms, plus the higher power in h terms. So you get 19.4481. Okay? And you're probably thinking, why didn't you just put that into the calculator, right? 2.1 to the fourth power, 19.4481. Well, because this formula that we're doing, the expansion, is showing us how to break the problem up into smaller pieces, right? And those smaller pieces, 4481, okay? Right? You may as well, this is a small number. The higher power in h terms lead to a small number. So it's possible, what we can say here is that 2.1 to the fourth power is approximately just the 19.2, right? If you take the higher power in h terms, you're going to get a more exact answer. You're going to get exactly equal. But if you drop those higher power in h terms, then you can get just an approximation, which is pretty close to the answer. Okay? So that is what we're saying here. We're going to say that if you're given a function f of x, it is possible, if a function is given to you, it is possible to approximate the function f of x plus h by just approximately writing the function evaluated x plus the derivative at x multiplied by h. That's what we're doing right here by just looking at the first three terms. The first three terms of, the first two terms right here will give you an approximation to f of x plus h. Okay, and we've shown how that works in the example of f of x is equal to x to the fourth. Okay, this doesn't stop with just the formula f of x is equal to x to the fourth or polynomials. It can extend to any other function. Let's say that you have f of x is equal to x over, say, x plus 1. And you've chosen a value of interest, a is equal to 2, and you're being asked to find an approximation for the function at 2.01. Find the answer approximately. Well, all you need to do, according to the calculus formula, is to do the function evaluated at x plus the derivative evaluated at x multiplied by h. And what we're seeing here, our point of interest is 2, so we need to put the function evaluated at 2, the derivative evaluated at 2, and then a particular value of h. How do you find this h value? Well, notice that you were given a point of interest is 2, and then you were asked to find the function value at 2.01. 2.01 is the value that you're interested in plus a wee bit more, which is 0.01. Okay, so this was your point of interest A, and the other number is the H. So we're seeing 2.01 is the A value plus H, where H is equal to 0.01. So now what you're being asked to do is to take the function f of x, put 2.01 into it, and that's approximately, you can put 2.01 into the function, or you can just put in the function evaluated at 2 plus f prime of 2 times the small difference at your point of interest. So the function evaluated at 2, I don't need a calculator for that, it's just 2 over 3. Then I need the derivative evaluated at 2 times 0.01. And here's where your work is going to come in. You're going to have to find f prime of 2. But first you're going to have to find f prime of x, and you're going to need to use the quotient rule at that point. Okay, and I'll just go ahead and get the answer there really quick. I'll leave you to look at the video on the quotient rule, and then you can find f prime of x. Okay, here is the function, here is the function's derivative. Okay, and then you need to substitute x being 2 into the derivative, and you get 1/9. Okay, so the derivative at 2 comes out to be 1/9. Okay, the derivative came out to be whatever it came out to be equal to. Okay, I will put that back on the screen so you can see it. It came out to be 1 over 1 plus x plus negative x over 1 plus x squared. That's what you get from the quotient rule. And therefore the function evaluated at 2.01 is equal to 2/3 plus 1/9 multiplying by 0.01 is same as tenths hundredths, 1 over 100. So that's 2/3 plus 1 over 900. Yikes. Common denominator of 900. Okay, it means I need to multiply by 300, so that would be 600 over 900 plus 1 over 900. So the approximate answer is 601 divided by 900. The function evaluated at 2.01, I should be very careful here when I say that's approximately 601 divided by 900. Okay, so I mean, I know that you can put 2.01 into the function, right, to get 0.667774. But that's approximately equal to 601 divided by 900, okay, 0.667778. And you can see that those are very close to each other. Okay, so the function at 2.01 is 0.667774, but the approximation, that's approximately equal to 601 divided by 900, which is equal to 0.667778. And we'll need this approximation idea quite a bit, which is why there are additional practice problems for you to do in the notes. All of these are saying find the approximation of the function near the point of interest, and they want you to find this function value approximately. And when they say linear approximation, they want you to do the formula f of x plus h is approximately the function evaluated at x plus f prime of x multiplied by h. That's what you're being asked to do. So I will leave you to try these additional problems, and this video hopefully you found helpful.